So this chapter, what we're going to focus on is linear second-order differential equations. I say that until Friday. Friday, we're actually looking at higher order that are linear as well. But our goal is to focus on the second order, meaning the derivative is the second derivative, differential equations. And the most general form that you're going to see of these differential equations is going to look like this. So if we have some function, this is what it would look like. Something like that would be the most general linear second order differential equation. I know everybody's favorite is the word linear. Now, if we assume constant coefficients, then a non-homogeneous second order differential equation is going to look like this. It's going to be A times y double prime plus b y prime plus c y equals some function with respect to that independent variable. Now, what we're going to look at initially to start with is the homogeneous equation, and that's where that g of x, I put g of t, apparently I changed the variable, is 0. So really what we're going to focus on right now is equations of this form. We're going to start with constant coefficients. We'll move into non-constant coefficients a little bit later, but we're going to start with constant coefficients. Okay, so let's start by thinking about solutions that will work with this problem. Okay, can you think of a solution, a function, that when you take the derivative and when you take the second derivative, it doesn't actually change?
Or zero and anything of the form a e to the f.
Okay, 0 doesn't change, right? So we know the solution. If I look at the solution y of x equals 0, this is actually what we call the trivial solution. That's always going to work. If our function is equal to 0, the differential equation that we're working on is equal to 0, and the function is equal to 0, those two are going to be equivalent. But you're right. The other solution that makes sense for us is going to be in the form of e to the x or t or whatever power we want to work on. It looks like I used t. I don't know why I used t on these notes. It must have been what I was looking at. X or t, they're the same thing. Okay, so we know the trivial solution, but let's think about this. Can I multiply that trivial solution by a constant and have it be the same thing? Okay, so if I change this and I said, okay, let's consider this to be a solution, y of x to be a solution, what if instead I multiply it by some constant c1? Could c1 times y of x also be a solution? Is it? Or would it be? If I multiply it by a constant.
It's a solution if and only if y of x is also a solution.
Right. If y of x, yes. If y of x is a solution, can I multiply it by a constant and have a solution as well? Now, will that hold whether or not I'm using the trivial solution? Let's try a different solution. Let's say, for example, I want to use g of x. And I'm going to tell you that assume g of x is a solution. Okay? If g of x is a solution, is c times g of x, some constant times g of x, also a solution? Okay, we know for the trivial solution it works because what happens when I multiply a constant by 0? we still get 0. So regardless of what I plug in there, it's still going to be 0. But does it hold for any solution? So if I substitute that in, c times g of x, we'll just call it c. I would have a times c, some other constant, maybe because we had a product rule in there, or sorry, a chain rule in there, would be g prime of x, plus b times c g double prime should have been in the beginning, sorry. This is just g prime, plus c times the other c, I should have labeled these c1s, so you can't get them mixed up, times g of x. Will that equal 0? Well, look at it. If we know that g of x is a solution, then we know this statement has to be true. And if I could factor out some constant, a times g double prime of x plus b times g prime of x plus c times g of x, is that a true statement? Is some constant times 0 always going to be 0? Yes. Okay, so that leads us to this principle that we have. It's called the Principle of Superposition. And it says if we know solutions, if we have some solutions, y1 and y2 that are solutions, and we know they're solutions, then any constant times y1 or any constant times y2 is also a solution. But it takes it a step further and says that if we have any solution, we can take and add the two solutions together, multiplied by their constant, and they will also be a solution. So if we know y1 and y2 are solutions, not only is y1 a solution, but c1 y1 is a solution. Some constant times y1 is a solution. Not only is that a solution, if we know y2 is a solution, c2 times some constant times y2 is also a solution. And then that principle of superposition says that we can add them together. Yep.
So that implies that you can add an infinite number of them.
It does imply you can add an infinite number. And get ready, when we start moving to higher order, we just keep adding things to it.
So there's an infinite number of solutions to any given homogeneous second-order differential equation.
Yes.
So how do we solve them without just giving a trivial solution?
So we're going to deal with the other equation that you mentioned earlier. What did we say the other thing that would not change very much when we take first and second derivatives? E to the x, okay? We're going to assume that everything else is going to be in the form of y equals e raised to the rt. And that C1, Jake mentioned a, e to the t. He's not wrong. But that a is going to be accounted for with our C1 and our C2. And C1 and C2 are what we're going to solve for when we do our initial conditions or our initial value problems. You will also start to hear the phrase boundary value problems. And all that means is we're giving you some value that happens to be on the boundary or the solution itself, the equation, the surface that we're dealing with, depending on what order we're dealing with. So boundary value problems, initial value problems, all are very similar. Now, let's verify this actually works, okay? Does this solution actually prove true if we were to plug it into this equation? So let's start with the fact that our y is e raised to the rt. If I were to do y prime, what is it going to be? Re to the rt. Assuming r is a... And then what is y double prime? R squared e to the rt. So... Get ready. We love quadratics. Okay, so this is going to lead us to how we find our solution. I'm going to substitute this in. So a times y double prime, r squared e to the rt, plus b times y prime, which is r e to the rt, plus c times y, which is e to the rt, and that needs to equal 0. So,
Does that mean we're gonna get into like complex?
oh, yes.
And then we're gonna have to
Look at Wednesday.
Uh-oh, okay. So, yeah, it was either like the I, theta, that definition.
Yup. Sure is.
That's gonna be fun.
It is fun. I actually really enjoy this unit. I actually think, for those of you that love your follow these steps and this happens every time type of problems, like this will be your jam. This unit is easier to follow because we follow certain steps all the time. Okay. Here we go. What do you notice? Well, I can factor out an e to the RT. And doing so, we would be able to use the zero product property, except I just made a statement that makes no sense.
Can e equal to the other t equal 0 for the imaginary other?
No.
So it can equal 0 plus some imaginary.
Correct. Can e to the RT ever equal 0? No. There's no way that that'll ever equal 0. Therefore, in order to solve this expression must be solved if e to the RT is going to be as a solution. Is going to be a solution. Okay, this has a special name. This is what we call our characteristic equation. Actually, I saw another name in a book that I was surprised by that I hadn't seen. Now I don't remember what it was. I told myself I'd remember it. This is your characteristic equation, or the book that we happen to be in defines it differently. They define it as 4, 3. Don't remember where we're at. 4. It defines it as, I don't know, I read it and I was like, huh, I've never heard that. But I don't remember where it is.
Kind of tired.
You're tired?
What? Sleep.
Shoot. Complimentary.
Well, English reading. Just reading. Are you guys doing groups and rest still? Yeah.
Well, shoot.
Yeah.
I do not remember what they called it. When I find the name, I'll tell you. But I thought, that's weird, I've never heard it. I've always called it the characteristic equation. So that's what we're going to call it. When I find the name that this book calls it, I'll reference back to it. All right, so our characteristic equation, you guys, is just a simple quadratic. Now, we know quadratics, and we know well enough to know that they're not all actually that simple. So this characteristic AR squared plus BR plus C is what we have to solve in order for e to the RT to be a solution. So we have 3 cases. We're going to look at case 1 and case 2 today. So case 1 and case 2. The first case is that we have real distinct roots. The second case that we're going to look at is repeated roots. What happens when we have a repeated root? And then case 3 that we'll focus in on Wednesday is our complex roots. So, case 1, that's what we're going to look at today. Real distinct solutions, okay, or roots. So the general solution is in the form of C1 e to the R1t plus C2 e to the R2t. It looks terrible. I promise you'll get the hang of it real quick and you'll see how it works. Okay, so here's the process we're going to go through. When we have a homogeneous second order differential equation with constant coefficients. Notice our coefficients are constant. It looks like a quadratic to begin with, right?
That's cool.
So here's what we're going to do. We're going to take a shortcut eventually. And I'm going to show you where that shortcut comes from. But the shortcut that we're going to take is we are going to change this into the equation r squared plus 3r minus 10 equals 0. Let me show you why we're going to make that jump. R is part of our solution. So here's why we're making this jump. If we assume that e to the RT is a solution, then y prime would be re to the RT, y double prime would be r squared e to the RT. And if I made a substitution in for y prime, and y double prime, we'd end up with r squared e to the RT plus 3r e to the RT minus 10 e to the RT equals 0. And then what would we notice? Well, we would notice that we could factor out an e to the RT, and I'd be left with r squared plus 3r minus 10. So every single time, if we're assuming that our trivial solution is 0, we understand that, but our other solution is in the form of e to the RT, making this substitution, this is what we're going to get every time. So can you go through these steps? Yeah, you can. Do you want to? Probably not. So I'm going to make a jump to say that what I'm trying to solve is this r squared plus 3r minus 10. Hopefully at this point in our life, we're pretty good at solving that, although it's been a while. Can we factor? Do we remember factoring?
No.
Whew.
I just used my calculator.
So we would get that r equals -5 and r equals 2. Once we find those r values, then it's as easy as writing our general solution. So our general solution, I hit my elbow this morning really bad, and it hurts. You know the funny bone that you hit and it's not funny at all and it brings tears to your eyes?
Yep.
I didn't expect it to hurt the rest of the day.
It's funny for everyone else.
It is, because you're But I was already mad because Aaron was complaining. I don't want to be here. I want to be in California. Why don't we move to California? So then I showed her house prices. I said, we can move to California, and what we can afford is this. Do you want to live there in that apartment? No. Okay. She thinks if we lived in California, we'd go to Disneyland every day. I don't know. I think the novelty would wear off a little bit. All right. Here's my general solution. Watch how nice this is. Once I know my r's, my general solution is C1 e to one of the RT plus C2 e to the other RT. And I'm done.
That's fancy.
So much nicer than say our exact equations from last unit, don't you think? Now, that's a general solution. Sometimes we're given initial values. So let's look at what happens when we have initial values. Okay? I want you to solve this and get a general solution. Will you solve this and get a general solution? Hopefully you remember your factoring. And yes, you can take shortcuts. Did we get the general solution of y equals C1 e to the -3t plus C2 e to the 3t? Those could be in any order. If you had C1 e to the +3t, you're still correct. It doesn't really matter. Now, how many initial conditions do we need? We need 2. Because we're dealing with 2 derivatives, we need 2 initial conditions. So the first thing that we're going to have to do actually creates more work initially. What we need to do is use the first initial condition. We can use this one. Let's do it in a different color. Let's use this one, and I can use that with the equation we were given. So I can make a substitution in 2 equals C1 e to the negative 3 times 0 plus C2 e to the 3 times 0. And what I get is 2 equals C1 plus C2. Well, the problem is I can't solve that. There's nothing I can do with that, which is why we need a second initial condition. And so my second initial condition, I have y prime of 0 equals negative 1. Guess what that means I need to do? I need to take the derivative of this, which gives me negative minus negative 3 C1 e to the negative 3t plus 3 C2 e to the 3t. And now I can make my substitution in. So we get negative 1 equals negative 3 C1 e to the negative 3 times 0 plus 3 C2 e to the 3 times 0. So I get negative 1 equals negative 3 C1 plus 3 C2. Now, look what I get to do again. System of equations. So I've got two equations here that I'm going to work to solve. Move my page up a little bit. So 2 equals C1 plus C2. You know what I probably should have done? Let's change that. Let's multiply that by 3. So 6 equals 3C1 plus 3C2. And negative 1 equals negative 3C1 plus 3C2. So we end up with 5 equals 6C2, which means C2 equals 5, 6. And then 2 equals C1 plus 5, 6. 2. 12, 6 minus 5, 6. So C1 equals 7, 6. How do we do? So while my general solution... Did I do my math okay? While my general solution was C1 e to the negative 3t, now my C1 for this particular solution is 7, 6 e to the negative 3t plus 5, 6 e to the 3t. It's going to be a long day. And there's my particular solution for those initial conditions. See, that's not so bad, right? Okay, let's move on to repeated roots. And let's go